Welcome everybody. Nice to have you here and appreciate your investment in time in learning something with me today. I'm going to talk to you about local seismic hazard mapping or regional seismic hazard mapping, particular to the Metro Vancouver region that I've been working on with my team for 7 years now, but also give you a sense as to other seismic hazard mapping that's been accomplished at the regional scale elsewhere in Canada as well. So I need to start with explaining seismic hazards, just to make sure we all know what I mean. When I say the word seismic hazard, I immediately think of ground shaking or ground motions. And that term can mean a lot of things. Seismic hazards can incorporate even ground deformations or tsunami waves. But in my discipline, we often just summarize it down to just mean ground shaking or ground motions. But it is more encompassing than just that. Seismic hazards are all kinds of hazards that relate to earthquake propagation and the shaking that results. The types of seismic hazards that we can deal with in terms of a regional seismic hazard map currently are to display shaking hazards and hazards related to liquefaction and landslide, whether they've been induced or triggered by earthquake shaking. And then for shaking hazard maps, we can display the absolute shaking amplitude, but oftentimes in microzonation mapping, we're talking about whether the amplitude has been increased or decreased or how it's been altered by subsurface ground conditions. And often that needs to be relative, or it's an amplification factor. It's a unitless number based on a chosen reference ground condition, or we're relating them always to the same denominator or the same thing. For ground motions and ground shaking, the best example I can walk you through, which is quite classic in terms of including not just the effects due to the soils, but also the fact that you might be in a basin, is the 1985 Mexican Mayachin earthquake magnitude 8, which affected Mexico City. So this earthquake happened on the interface fault 400 kilometers away from Mexico City. And so the shaking should have been reduced for having traveled 400 kilometers. But as it entered Mexico City, it was quite low intensity shaking on the rock at the edge of the city. But as it propagated into the old lake bed basin beneath Mexico City, which had been drained, and now the city has been built on top of that, the seismic intensities increased because the sediments are softer, and also increased at a particular period or a particular frequency or a particular wavelength related to the material properties of that basin. And so in the example of the time history in the top left, you can see these nice big squiggles. And in 10 seconds, you would have experienced 5 crests of a wave, or the feeling of a 2-second period wave amplification. And the problem is that particular filtering of the seismic energy by the subsurface ground conditions feeds in amplified motions at a particular period range, but also would resonate with structures that have that same particular natural vibration period. And so in Mexico City, we saw mid-height structures, 8 to 10 stories, predominantly collapse from this shaking event because of the period at which that shaking was being filtered. And so this is a combination of the fact that the site conditions, soft sediments, but also 3-dimensional basin effects. You're inside of this basin, the energy is trapped, and it's being amplified at a particular period range. Mexico City now designs according to particular zones, if you're at the edge or in the transition or in the deep basin. For seismic hazard and liquefaction, what I mean is the ground, which we think of as very solid, can behave like a liquid during earthquake shaking. This is because, particularly if it's very sandy or granular, there'd be water between the pores. And as you compress and expand it while the earthquake is shaking, you can't compress water. It needs to go somewhere. It'll try to make its way up to the surface, bringing that sediment with it. So liquefaction manifests or appears as the ground bubbling up with water and sediment. And the most dramatic example of that is the picture on the bottom left from the 2011 Christchurch earthquake. Bringing it back home to BC, we've had strong shaking in the past. The last megathrust earthquake of 1700 plus events that happen on a recurrence interval of 500 years, we do find evidence if we dig underneath Metro Vancouver, we can find places where we see sand percolating up through the layers, and we can date them and decide that it's relatively reasonable that these were the same timing as these past megathrust earthquakes, or maybe a shallow crustal earthquake nearby. So I've told you that liquefaction will result in the sand bubbling up or coming up to surface. So you're going to have to remove all that material after the earthquake. You're also going to have settlements, which will lead to buildings, foundations, roads, readjusting to that new deformation or displacements that have occurred. What's also interesting is that if you have something underground, like a pipe or a sewer or a manhole, it's also going to try to come up to surface just like the sand. And so you'll have these displacements in the utility infrastructure that was underground as well. Our last type of seismic hazard that we're going to review and then also try to map regionally is landslides. And landslide is simply a big blanket umbrella term for me to refer to all types of ways in which material will make its way down slope under the force of gravity. And if it's rock, it probably would fall or topple. If it's more dense, stiff earth material, it might slide or spread. And then if it's more water laden, like a mud or debris, it might flow. And so when I say landslide, I mean all these types of ways that these different types of material will move down slope. And again, some images there trying to bring it back home that we know that landslides have been triggered by earthquakes in the past in BC. And so as we move material from high elevations to low elevations, that material is going to end up on our roadways and our waterways and lead to issues and complications. The bottom right image, it's not immediately clear that there's these white pipes that have been broken and displaced behind this retaining wall. So now it's time for me to discuss what regional seismic hazard maps are, or give us a background on seismic microzonation mapping. So the first take-home key piece of fact is that earthquake shaking is not uniform ever in any earthquake due to variation in local site conditions. The shaking intensity where I'm standing is going to be different from the shaking intensity somewhere else, simply because there's a distance between those locations, so that attenuation or energy will decrease as it travels further, but also the fact that the waves have to propagate through and up to surface through the material that's present there. And that's going to change to the earthquake shaking or cause alterations. And so when we're doing seismic microzonation, our purpose is to try to make maps or zones on a map that identify it's going to be similar shaking here because the subsurface ground conditions are similar, and it's going to be different from over here because those ground conditions are different. And so that's simply what seismic microzonation maps are trying to convey, is that these zones or areas in which the earthquake hazards are similar but different from somewhere else. We use maps because they help communicate this extensive and complex information in a relatively compact product. I can take everything that's happening in the subsurface and try and map it just from above. And we need maps to play a critical role in making this information available to you to be able to use in your decision making. In order to make these maps, we're going to need a lot of information about the subsurface in terms of its geology, what it's made of, in terms of its geophysics, how stiff or strong it might be, and in terms of its geotechnics, how it's going to behave under strong shaking. As well as we're going to need to perform some sophisticated seismic hazard analyses or numerical modeling to predict that ground shaking. This is a complicated slide a little bit, but on the left, we have site-specific seismic hazard assessment, and on the right, we would have our national scale seismic hazard assessment. And microzonation mapping is going to be in the middle. It's going to be regional scale. And so as you push to higher or to greater scales, as we go from site to region, in a region, we're considering thousands to millions of sites. And at the national scale, because Canada is so big, we're considering millions to tens of millions of sites. And so I think it's understood or logical to assume that how accurate we can be in that ground prediction is going to decrease as we push to bigger scale. And we're also going to look for ways to simplify how we're predicting that shaking or the effects. And so microzonation mapping is somewhere in the middle. It is more accurate than national scale seismic hazard mapping because it takes more information about the subsurface into consideration. It's less accurate than site-specific analysis, so our region-specific maps do not replace design based on the detailed information that you have at the site. But maybe one last way to try to sell it to you is our regional map considers site-specific assessments wherever we have data. And so it is as accurate as site-specific seismic hazard analysis for that location that we had information. But then we have to figure it out regionally, or correlations or spatial variations, in order to depict it for the whole region. And so that's where we lose some of that accuracy. And so one last big piece of information about regional mapping is that it also has levels, or it can get more and more complicated the more data you would have. And in international standards, they do just describe it as these kind of 3 levels. As you increase the quality and quantity of the data, you can push to better and better mapping with more and more detail. So at level 1 or 2, we're talking about the susceptibility of the ground. Is it susceptible to being shaken at 2-second period? Is it susceptible to liquefying? Only to when we get to level 3 are we doing that sophisticated seismic hazard analysis to really predict what that ground shaking will be or whether that liquefaction will be triggered. And then last but not least, you can imagine that the time, effort, and energy involved to create a level 3 seismic microzonation map is much higher than that of a starting point, a rough guess, a qualitative type analysis at level 1. And so the last way to try to explain it is you don't do level 3 seismic microzonation mapping overnight, or you don't start there. You kind of build up towards it. I think it's interesting to show you that we've had a history of producing shaking estimates in Canada since the 1950s in terms of a national seismic hazard model, and therefore seismic design ground motions in our building and bridge codes. This is redone on a 5-year annual cycle. We, in contrast, or to try to place regional scale or local seismic hazard mapping inside of this evolution, is that we've been producing these maps since about the mid-90s in Canada. And you can see, I'll make a point in another couple slides, that these maps on the bottom, you can see that they're all different colors. But technically, all these maps are depicting seismic site class or the same measure. And one of our problems in Canada is that we don't have a standard approach to making these maps. And as someone who makes maps, I certainly enjoy being creative and choosing whether it is colored red or purple. But I understand now that that's a problem for use or comprehension. If I make the map and I say the site class is a certain color and the next map next to mine uses a different color, well, it takes a second to understand what you're looking at. So these are some key facts about seismic microzonation mapping in Canada then, harping on this idea that there is no Canadian standard or guideline. The list on the right shows that there's all kinds of region-specific seismic hazard maps that have been created for regions in Canada. But you'll notice that in the previous slide, they were all different colors, and there's no standard then. These existing seismic microzonation maps are also accessible and are not accessible in digital or GIS layer form up until now. Every creator here has produced them and published them, and sometimes they're just a small figure in a journal article. If they're made by our federal government, they are sometimes very nice big maps, and you can download them online, but it's a PDF file, and what do you really do with that other than look at it? You don't really overlay it with your assets or have a ready way to input it into your risk analyses. So these two big issues are essentially these hindrances to our comprehension and use of region-specific seismic hazard mapping in Canada, I would say. And then last but not least, I want to harp on the fact that there's very few high-level seismic microzonation maps in Canada. On the right, the type of mapping that's been done is usually site class, VS30, the average shear wave velocity of the top 30 meters, or T naught, known as site period, or how the ground vibrates, at what period does it vibrate. All three of those are just susceptibility to shaking. That's only level 2. We do not have very many level 3 region-specific seismic hazard maps. Another way to say it, all these studies on the right have done a very good job of trying to document what's going on in the subsurface, but they haven't pushed it as far as predicting what that subsurface ground conditions are going to do to the seismic shaking, or will landslides or liquefactions be triggered. And so ultimately, we have little experience up to now in accessing or using level 3 seismic microzonation maps. So this leads me to ask you a question. And I think I'm waiting for Winnie to share that on the slide for you. Yep. So are you aware of the available seismic microzonation maps in Canada? And I didn't think ahead of time. Now you are. You've seen the table that I just showed you. But my question is really, were you aware of these available seismic microzonation maps before we got started? So no, I'm not aware of these Canadian seismic microzonation maps. About 80% of you are saying that. 17% are saying that you knew a few of these Canadian seismic microzonation maps. So that's fantastic. 2% of you are saying you knew about many of these Canadian seismic microzonation maps. So that's great. There's some key nerds in here. That's fantastic. And even 2% of you are saying you're aware of and have used some of these maps, and that's fantastic as well. So I guess I'll move on now. Thank you for that. One last homework that we have to do together here to set the stage is that if you read about seismic microzonation mapping in the world, everybody says they're so fantastic and everybody can use them, especially technical experts in earthquake engineering or CAT modelers or risk analysts. They're going to use this product to inform disaster risk reduction and improve their understanding of the regional seismic hazard. And I think, yes, that's generally true. We start to fall off here in terms of pushing towards intermediate users. So for example, an emergency manager or a building owner, they are supposed to find these maps super helpful for emergency response and recovery planning. But I would say that's not actually the case in practice. And then last but not least, we do make these maps or images available, freely available. And so anyone can come across them and try to use them in any way they choose. So just harping on this idea that in terms of technical experts, I think they are technical expert in terms of whether or not you understand seismic hazard or how seismic hazard is predicted. Are better set up to understand these hazard products. But honestly, even structural and geotechnical engineers have a bit of a hindrance because they do it at a site-specific scale, and they don't really think about how to map that out or make it simplified guess regionally. And so I would say there is this quite strong hindrance, or there's this issue in producing these maps, is that they're going to be misinterpreted or potentially misused or just sit there and no one knows what to do with them because it is a very complex technical type of hazard to convey. But the people who are using them, the disciplines that want access and need to use them, is a bit too wide or too much for the intended use of these maps. So with that background, I thought it'd be interesting to give you a sense as to, let's compare what you would get out of a level 1 type map compared to what if you did a level 2 type map. So I want to hammer home, what do you have available right now as an insurer in Canada? You could go online and you could access these region-specific site class maps for these 6 Canadian cities. And they're level 1 to level 2 in that they're based on some measurement of the subsurface ground condition in that map. As opposed to, you're an insurer and you're sitting in your office, you also have access to download or look at the United States Geological Survey Global VS30 map. There's a map of what VS30 is, or seismic site class is, for the entire world. And you can access that online. The problem with this map is that it's just a proxy. Nobody went and did this measurement. It's just an estimate of how stiff the ground would be based on how steep the slope is. And so places with high steep slopes, high elevations, have higher VS30s, or stiffer ground conditions, or rock-like conditions. And places that have low elevation or are not steep slopes, shallow slopes, would be softer or lower shear wave velocities and softer soils. But this is just an estimate. And it's a quick and easy estimate to make. But as we see in Eastern Canada, we see a shift kind of towards the fact that this topography estimate is going to predict lower or softer ground conditions than what we actually measure in Eastern Canada. And if we propagate that to level 3, or trying to predict what the seismic shaking would be, in general, we're talking about we would overestimate the seismic shaking based on that topography estimate. And so our seismic design would be too much or too conservative. We would be overbuilding. As opposed to in Western Canada, we see the bias is towards that the topography estimate is predicting higher or stiffer seismic site classes than what we actually measure in Western Canada. And so propagating that through to predicting shaking levels, we're talking about that we would be underestimating the shaking level, and therefore our seismic design would be unconservative or not enough. One last thing to try to hammer home is that in Eastern Canada, a topography-based level 1 rapid, I don't go there, I don't do the measurement type of assessment, means that the map is only 15 to 30% correct. In Western Canada, there is more elevation. There's tall mountains, there's low lows. And so this topography-based estimate is a little bit better. The map could be 30 to 60% correct based on that quick estimate. But I'd like to hammer home the point that if you're not going and doing the measurement at that location, you're not going to be accurate enough. You're going to have a quick, rough estimate, but you're only going to be right about 30% of the time currently for seismic site class in Canada. So let's talk about trying to make a seismic microzonation map in Metro Vancouver. And we've been working on this for 7 years. We started in 2017. And so we're doing a phased approach to including communities as we move eastward. This summer, we're going to be releasing 29 region-specific seismic hazard maps for this phase 1 Western Metro Vancouver region. This summer, we continue collecting data and work on mapping for the eastern communities shown as phase 2 to release those maps in 2026. We are working on producing seismic microzonation maps that are going to display predicted variations in seismic hazards, specifically how the subsurface soil ground conditions can alter earthquake shaking, also how earthquake shaking might be amplified or increased because of the presence of Metro Vancouver sitting within a Georgia basin or a sedimentary basin, as well as also predicting whether or not landslides and liquefaction will be induced by the seismic shaking. So why does Metro Vancouver need these region-specific seismic hazard maps? I don't think it's a mystery to say that Metro Vancouver has the highest seismic risk in Canada. That's largely driven from the fact that it's sitting in Southwest BC at the northern end of the Cascadia subduction zone in an active tectonic environment. We have many earthquakes happening that contribute to that hazard, but that makes it technically challenging to try to produce these maps or anticipate seismic hazard in Metro Vancouver, more so than, say, Eastern Canada, where there's one type of earthquake. In Metro Vancouver, we also have a crazy range in what the subsurface ground conditions are like. We can have sediments that are 300 meters thick, a kilometer to rock, and it's sitting this, we have a basin sitting inside of a basin. And this situation is completely different from many other places in Metro Vancouver. So this has been one of the major hindrances why I showed you there's other maps that have been made for other cities, and pieces of this evidence has been produced for Metro Vancouver or particular cities within Metro Vancouver in the last few decades. But nobody's ever systematically tried to do it for all of Metro Vancouver, and also tried to push to this level 3, or really, will liquefaction be triggered? Will landslides be triggered? What will the shaking level be? Rather than, is it susceptible? So a couple more details on this highly variable seismic site conditions. Metro Vancouver sits inside of a late Cretaceous sedimentary basin. So there's rock under Metro Vancouver, but it's kind of soft rock. And then glaciers brought down debris from the mountains and deposited into the hills of Vancouver, Burnaby, and Surrey. But then also in the last 13,000 years since the last glacier advanced or retreated and started to melt away, the Fraser River Valley has been bringing sediments in and depositing a delta in the Fraser River up to 300 meters thick. And so it's these ranges, it's the scale and the range and the subsurface conditions that's unusual for the rest of Canada. We've had to persevere or overcome these technical challenges in creating these maps. One other area in which there's complications or complexity to predicting the seismic hazard is the fact that we can have earthquakes happening in 3 different source areas, and therefore happening at different depths and different occurrence rates. But that comes from the 6th generation seismic hazard model produced from the federal government. And it tells us that we can anticipate shaking in Vancouver to be about 0.19 G at short periods. And this is greater than 0.1 G, and 0.1 G is around strong shaking, or when damage will start to occur. So we can anticipate strong shaking in Metro Vancouver to occur on a 10% probability of exceedance in 50 years to exceed that strong shaking level. But because we understand these earthquake occurrences, we can look at any kinds of return periods or any kind of annual probability of exceedance. And any time you would look at a longer return period or a shorter annual probability of exceedance, the hazard would go up, or that the intensity would increase. My purpose here is to set the stage that we're going to look at seismic hazard maps for 2 different return periods, or 2 different intensities of shaking, for a 475-year and a 2475-year return period. And ultimately what that means is that the one map is about 2 times or 2.5 times stronger shaking than the other, or the input of the seismic intensity had increased that much as we move to the longer return period. Last but not least, since you're insurers or reinsurers, I talk in hazard, and that's what the maps are showing. But if we try to translate that to risk, the best I can do for you right now is to say that there was a study back in 2005 of the monetary losses just for the city of Vancouver, and they predicted about around 2 billion in insured losses. If I use a factor of about 30% of the total monetary losses, insured losses. And the most recent studies there's a national seismic risk model created by the federal government very recently, and they anticipate the total monetary loss for a 500-year return period for British Columbia to be almost 9 billion, let's say, in insured losses. And so Metro Vancouver is somewhere within here. It's going to be bigger than just the city of Vancouver itself, but it's going to be smaller than all of British Columbia. But on a scale of what's happening in terms of paying out insured losses for hazards in the last few years in Canada, we are talking proportional to bigger than the normal 3 billion in insured losses that are happening annually for other hazards combined in Canada. If a 500-year type earthquake occurs for Metro Vancouver, it's going to be something we've never tried to pay out before. And then lastly, if we maybe push that 2475-year return period, or a very rare type of event, it seems exponential from there, much higher. So I want to introduce you to some key outcomes that occurred during the project before I get into how we made the maps.
Sherry,
So,
we're at 30 minutes.
thank you. Yep. So I think I've hammered home that we're pushing to level 3 or seismic microzonation maps, and that's relatively unique in Canada. But we understand some hindrances to comprehension and use. So we've set up a professional practice in 2 different ways. One is that we had technical peer review, and another that IIBC engineers and geoscientists of BC have developed professional practice guidelines on how to develop and use these maps. And so we're pushing towards those Canadian standards in the long term. And then to promote comprehension and use, we also have included regular engagement opportunities during the project and involving a non-technical user in our peer review process. And that's not a common occurrence for seismic microzonation mapping projects in Canada. It's also led to a new workforce that has worked together on trying to understand regional seismic hazards. And so it's taken multiple disciplines and multiple experiences and also a pretty cool project to have worked on if you're a grad student in Canada. Now, here we go. Here's the key outcomes of the project. We've created 29 maps. Here you can see 11 maps that are only level 2 or only an indication of where the ground might be susceptible to liquefaction or landslides, where the ground might be susceptible to increasing amplitudes of shaking or decreasing it, or what kind of period range that might happen, and where the Georgia Basin is relatively deep, and therefore where 3D basin shaking might be susceptible. We also pushed all further to level 3 maps, and now we're talking about the last 18 maps that are made for a particular seismic shaking intensity or a 475-year return period. And here we're predicting that liquefaction will occur or will be triggered by that shaking intensity level, or landslides will be produced, or that the earthquake shaking will be increased in oranges and reds or decreased in yellows and greens based on that shaking intensity. And we do look at it at the 2 different return periods or for those 2 different shaking intensities. And lastly, the map depicting where we'll see increased shaking at long periods related to the 3D Georgia Basin. So that was a quick preview of where we're going and quickly how we did that. So we needed to collect information about the subsurface. And so we pulled information online. We also asked existing engineering firms or cities for access to data that they had collected over the last few decades and converted that to digital files in our database. The project also supported going out and doing measurements, pushing for good quality and good quantity data behind these maps over several summer field campaigns. And we can quickly measure what the filter effect of the ground is like to seismic shaking. We can also try to understand what the detailed stiffness structure is like at locations in order to make sure that we have data behind the map regionally everywhere. For seismic hazard mapping, we are depicting the fact that earthquake shaking will be amplified, increased, or de-amplified, decreased, relative to a reference ground condition of dense, stiff ground. And so the maps are going to show how the ground could be amplified or the shaking could be increased due to just the soil column or just the fact that there's soft sediments, or also whether or not the 3-dimensional sedimentary basin structure increased that ground shaking. So we translate our geodatabase, essentially, what we understand about the subsurface ground conditions, into what types of materials it is, and therefore we can make a geology map. We can also translate whether or not the ground is very shallow or very deep. What's the depth to rock, basically? How stiff or how soft is it? And then a cool parameter, a site period, that kind of combines how thick it is and how stiff it is into one parameter. So that helps put 2 things in one map. and that you would experience relatively rapid or short period vibrations in northern Metro Vancouver, because the ground is generally stiffer and shallower there than it is in the southwest. But it doesn't answer this level 3. It doesn't answer how much the ground will actually amplify or de-amplify earthquake shaking. We have to consider a particular return period, or we have to consider a particular intensity of that earthquake shaking as it comes in. And so we need to input what that intensity of shaking will be. And we input that for 3 different earthquake types into 55 soil models. We run that 3 different ways, 3 different linear or nonlinear analyses, to end up with 11,000 answers to the shaking intensity across Metro Vancouver, which we then can build into these zones to understand what the amplification is like for each zone. And we can use that regional depiction of the subsurface ground conditions to map that out regionally. We also need to add the 3-dimensional basin structure, or what the underlying Georgia Basin will do to the ground shaking. And there's a video here that I'm starting. And this is for the 2015 magnitude 4 earthquake in 2015 below Victoria. So it took 10 seconds for the earthquake shaking to even reach the surface, because this is an in-slab earthquake happening in the subducting Juan de Fuca plate. And now the waves are propagating northwestward across this map, and Metro Vancouver is here. And the Georgia Basin is in the low water, Strait of Georgia, and as well as under Metro Vancouver. And you can see that basically surface waves get generated inside of this basin, and then they kind of get trapped and reverberate back and forth. And so you have these surface waves that just never leave the basin. And we've run these simulations for different types of scenarios, of different types of earthquakes at many locations. So we have over 300,000 estimates of what the shaking intensity is for these types of earthquakes. And we do some fancy math to make sure that we don't double count basin amplification on top of site amplification. But these maps shown here are showing you where in Metro Vancouver the long periods at 2 seconds on the left and 5 seconds on the right, where we anticipate shaking intensities to be stronger than what our current national seismic hazard estimates can predict. Basin effects are not included in the national scale seismic hazard mapping. This map is showing us where shaking intensities will be greater due to the deep Georgia Basin, but also in the uplands or the southern uplands of Vancouver, Burnaby, Surrey, and White Rock, because those are stiffer ground conditions and wouldn't normally have been predicted as having high amplitudes at long periods, but they're inside of a basin, and we have to add that back. Or add back that knowledge that these stiff sites are sitting inside of a basin. And so we've basically combined the 1-dimensional amplitudes that we predict with the 3-dimensional basin amplitudes amplification that we predict to create our final amplification maps at these long periods. In conclusion, we create 12 seismic shaking hazard maps, and that's a lot. One thing is that they're for 2 different return periods, so that doubles how many there are. And then another thing is we have to make them for different periods or different frequencies of vibration. And so we choose 5 spectral periods to depict these maps. Ultimately, northern Metro Vancouver starts off as orange or red, very high intensity of shaking at short periods, because the ground is stiffer or shallower in that area. And then down in the Fraser River Delta, where it's nice and soft and thick, we see potentially de-amplification or decreasing of shaking intensities at short periods. The long, deep, soft basin filters it out. It doesn't make it to surface, but it does preferentially filter and enjoy responding at these long periods of 2 seconds and 5 seconds. And that's where the amplification is happening. So now, we still have 2 other types of hazards to talk about. So liquefaction hazard mapping, we start with where is the ground going to be susceptible to that liquefaction? And so where it's young ground or young sediment, where it's sandy and where it might be water filled, are perfect proxies for understanding where the ground might be susceptible to shaking. But this is very qualitative. We also spent 6 to 7 years creating a geodatabase of measurements of the soil resistance under Metro Vancouver. So we can try to add columns of information as to how resistive the soil is, and therefore what its liquefaction susceptibility would be. So we make a level 2 map that is an approximation from the geology, but also verified or the colors are determined from this measures of soil resistance. And then, but we haven't answered the question of whether the ground will actually liquefy given the intensity of seismic shaking that might occur. And at a mean return period of 475 years, we're seeing that the Fraser River Delta will have liquefaction occurrence. We've determined this through understanding how resistive the ground is and to the input shaking intensity, and that's averaged over the top 20 meters. How much liquefaction is going to happen in the top 20 meters? If the whole 20 meters will liquefy, it's going to be a high number. If very little of it will liquefy, it's going to be a low number. And we determine that for the mean annual rate of exceedance of those ground motions, and therefore the mean annual rate of exceedance of that liquefaction at over 1,000 sites. This is being determined. For landslide hazard mapping, we follow very similar process. Where are there slopes? How steep are they? How weak is the material on that slope? And therefore, how much does the slope have in terms of a critical acceleration? If it has a low critical acceleration, I only have to push it a little bit to get it to fail. And therefore, it has a high landslide susceptibility hazard. But I also have a geodatabase. I can build two-dimensional numerical models to predict better what the critical acceleration is for these slopes, and have a more quantitative assessment of that landslide susceptibility. But will they fail in an earthquake? So at 475-year return period, the map is mostly yellow, or we see mostly low landslide hazard potential. At the mean annual rate of exceedance of ground motions and for the mean annual rate of the critical acceleration of these slopes, we determined that the return period, or for these two chosen return periods, we're not seeing significant displacements to lead to very high landslide occurrence events. But as we push to this 2475-year return period, the map starts to turn orange and red, and we start to see that landslides will be triggered more and more at that higher shaking intensity. Finally, we're here at another fun query for you. So I've been talking. Do you feel confident in understanding the differences between a level 1, 2 susceptibility map and maybe this level 3 hazard map? And you've been listening, because 86% of you feel confident now that you understand the differences between this low level of first pass seismic microzonation mapping and pushing it up to this level 3. Will it fail? What will the intensities be? What kind of effects will actually happen? So that's great. I'm glad that message came through. I've done my job. So I'm going to skip over some of these slides about engagement, communication, education, and training for time, I think. In that you've just answered this question. We also sent out a survey back in 2020. So I'm not surprised by the feedback that you've provided, in that I make seismic microzonation maps. So I'm very aware of them in Canada. But honestly, I didn't know all of them when I started working on this project. And then I am using and interacting with these maps the most, just like potentially technical end users or other hazard experts in seismic hazard. But as insurers, you might be very aware, in our survey, 60% of emergency managers or insurers were aware of seismic microzonation maps. But then it dropped to about half, like 30%, were only using or interacting with these maps. I'll skip this, sorry, quickly. Basically, I started with the idea that we are making these maps, they're very technical. There's this hindrance to comprehension and use, and we're trying to solve that issue in a number of ways through technical and non-technical peer review, talking to the earthquake engineering community back in 2023, hosting a workshop to explain the difference between liquefaction susceptibility and liquefaction potential, even back in 2023, and having these types of engagement sessions that we're having now together about the project. There have been professional practice guidelines, and they have just been published and available online late last week. And these guidelines are now a step forward towards having a national scale or nationwide standards and guidelines. But the guideline document, if you download it, you'll come across what kind of data, what kind of expertise, what kind of information is needed and analyses to perform and develop and make these maps, but also try to talk about a common approach for their use. And so these are some of the uses that are inside of these guidelines for these different disciplines. But for this audience, I've gone ahead and made some wild suggestions on how you might use these maps. So first and foremost, they're just hazard. And that's super not helpful necessarily in what you do. You want to know the risk and loss. And so these maps and the 7 years currently of knowledge behind them has to start infiltrating into new catastrophe modeling, and therefore risk and loss estimates that your company has access to. Another key take-home message is, even though there's 29 maps that try to explain where it could be better or worse or higher or lower or different, basically the fact that there's 29 maps for Metro Vancouver trying to talk about seismic hazard should be enough to try to push for a general uptake of earthquake insurance for all of Metro Vancouver. For me, the 2 different return period maps I think are beneficial, even though it's been a pain to have to make double the amount of maps and double communicating about that. But I think it's super important to have the 2 options in front of you to compare. And for me, I think it's helpful to try to reinforce, and in your industry, you deal with probabilities, you deal with return periods. So this is potentially intuitive to you, but for a shorter return period, if the map is already showing that the hazard is moderate, high, or very high, that's a problem. And that it's going to be higher for a even longer return period. And it's these places for a shorter return period, if it's already a very high hazard rating, we're concerned. We should start there. And the 2 return periods that we chose, 2475 is the reason. It's because that's used for building new buildings and bridges in Canada. That's the standard hazard level. And then for other natural hazards, we tend to talk on a 1 in 500 year type event. And so that was the other return period that was chosen. I'm going to even keep going and being crazy here in terms of what would a broker or how would insurance policies change. It's possible to use these maps now, I think, to prioritize or develop specialized policies for areas where earthquake shaking is expected to be increased. So for example, you could go even as far as for the north part of Metro Vancouver, you're going to develop a policy if that structure is the ground is going to shake at shorter periods. And if the structures or the assets that's exposed to that hazard has the same kind of response period range, well, that might be a problem and need a tailored insurance policy. I have absolutely no idea if in your discipline you go this granular, but you've never had these maps before to do that. So maybe you can. And then last but not least is the liquefaction and landslide hazard potential maps. Tell us where it doesn't happen everywhere. It's concentrated. And so it's in those areas that we might want to be selling additional earthquake insurance coverage or additional living expenses. for where the shaking and liquefaction and or landslide hazard will be together. In terms of risk profiling, I want to keep hammering home that we've just made hazard maps. They need to be pushed towards new improvements in risk, get filtered into CAT models. But I also need to hammer home that these maps are new and an update to what it has been available for seismic hazard in Canada till now, and that we're dealing with a regional scale, and so we have better site information, and we use more metrics to try to anticipate what the ground shaking will be than the simplified national way of doing things, or what a simplified code procedure is. And so that's important that these regional specific updates should be making their way into risk and loss estimations. And again, at the national scale, it's very simplified. We don't deal with the fact that Metro Vancouver sits within a three-dimensional basin. The fact that there are three-dimensional, and there is anticipation of what the shaking amplitude would be at long periods because of this basin has never been shared or produced before. And again, that liquefaction and landslide hazards are concentrated and don't occur everywhere. So quickly, how are you going to get your hands on these maps? We're going to make them as maps, as in just like everybody's made them before traditionally. The reason we do that is A, we get to control how they look. B, it's showing the colors that we realize are intuitive and have a standardized way towards those colors. And we get a chance to explain and make a very clear legend for you, which we found through consultation was desired. We also have a project website where we'll be making an open data portal where you can get these published maps coming this summer for Western Metro Vancouver, but also be able to interact with these maps online in a GIS environment. You can zoom in, you can zoom out, you can decide whether you want to download that GIS layer or overlay more than one of them together to take a look at that before you download them. The data behind, when you download a GIS file, you're going to get the map value in the attribute table. But if you want the information with depth at that location, you would have to access the geodatabase behind these maps. And so I know I took a long time, but the last message is these maps are coming to be released for Western Metro Vancouver this summer. And we keep going into Eastern Metro Vancouver to release those maps into late 2026. Thank you. I'm done.
Thank you so very much.